A mechanic is adjusting the brakes on a Cromwell tank, in the dark. His hands are on metal that is still hot. He knows what's coming. He does it anyway. His arms, his hands, his neck, all of it against steel that hasn't cooled. The infantry they were supposed to guide left 4 hours ago. There's nothing to guide now. September 22nd, 1943, Bovington Camp. Behind him, somewhere in a building with good light and bad news, a classified military trial has just ended. 1 month ago, 2 armored forces drove 2,000 miles. 1 arrived. 1 didn't. The mechanic doesn't know the numbers yet. He's got a tank to fix and it'll be ready by morning. That's his job. What nobody standing in that field tonight understands, not yet, is where those numbers are going, who is going to read them, and what exactly they're going to be forced to admit. The answer came in a report, 47 pages, classified, written by a major named Clifford, tasked with explaining what he'd seen to people who would not enjoy reading it. The trial was called Exercise Dracula, 6 weeks. Late August through September 22nd, 1943. 2 brigades of tanks, 4 different vehicle types, and 1 question that seemed simple until the data came back. How reliable are these machines? The Sherman Force, M4A2s and M4A4s, American tanks on British soil, covered 13,986 combined miles, 0.03 maintenance hours per mile, 199 confirmed defects across the entire force. Operational confidence, per the final report, approximately 99%. The Cromwell Force, 11,582 miles, 0.07 hours per mile, more than double the American rate, 367 confirmed defects. Operational status, in the exact language Major Clifford chose, a continuous state of anxiety. Then there was the Centaur, 8,492 miles, then pulled from the road entirely, loaded onto transporters, removed from the trial while the trial was still running. The Liberty engine powering it had been obsolete before the war even started, a placeholder in a tank that was itself a placeholder. And even that wasn't enough to keep it going. Those numbers look like a maintenance problem. They aren't. They are a symptom of something much older. The Sherman and the Cromwell were not different classes of machine. The generation of design did not separate them. Both carried a 75mm main gun. Both weighed between 28 and 33 tons. Both needed 5 men, a commander, a gunner, a loader, a driver, a hull gunner, and both had been designed, tested, and declared battle-ready before either crossed into a combat zone. On paper, Major Clifford was comparing equals. Everything about these machines, on a specification sheet, said so. Off paper, in the maintenance logs, in the defect tallies, in the hours mechanics spent beneath those hulls instead of sleeping, one of them demanded more than twice the labor to cover the same ground. That ratio is 2.3 times, 0.03 hours per mile against 0.07. Across 6 weeks and 11,000 combined miles, the gap added up to hundreds of additional man-hours, nearly double the confirmed failures, and a confidence so different it produced 2 separate kinds of commander. One who planned on his full strength arriving, and one who quietly hoped it would. This is not a bad batch of parts. Not a single error that slipped past an inspector. The gap is systemic. It runs back through each machine, through the factories that built them, all the way down to a fundamental disagreement about what making things at scale is supposed to mean. Major Clifford's 47 pages went up through the chain of command, from Clifford to Major General A.C. Richardson, from Richardson's desk across the Atlantic. American officers read the data alongside their own observers' reports, and what followed was not a polite conversation between allies. What Major General Richardson wrote back to Washington was not a commendation. It was a warning, and it would take 2 more years and thousands of broken tanks before anyone listened. The trial is concluded. The numbers are on record. 2.3 times. The same gun, the same crew, the same road, and results that different. But to understand why the gap exists, why it had to exist, you have to go back further than Exercise Dracula, back to a problem that Britain never fully solved. The problem Britain couldn't build its way out of was not a single flaw in a single tank. It was a culture, And cultures don't appear in engineering reports. They appear in the numbers those reports produce, year after year, trial after trial, until eventually, someone in Washington reads the results and uses a word that no ally wants applied to them. Richardson's letter used that word. It didn't circulate widely. It wasn't meant to. But the substance was plain. British armor, by the autumn of 1943, was being discussed in American military circles as an embarrassment. Not because British engineers lacked ability, not because British factories weren't running, because the tradition behind the blueprints was producing machines that could not keep themselves running in a war at industrial scale. To understand that, you need to know what a Birmingham workshop looked like in 1943, not a factory. A workshop, vaulted ceilings, long benches, craftsmen, skilled men, the proud men who had spent entire careers learning to make components fit by hand. A file, a chisel, a trained eye, and the patience to work a part until it seated correctly. This was not a failure of effort. It was individual craftsmanship applied to a problem that demanded something entirely different. Identical repetition, at volume, without variation, across thousands of vehicles instead of dozens. When a Rolls-Royce trained fitter assembled an engine, he made each part work in that engine, with those tolerances, by those hands. The result could be exceptional, and often was. But the moment you needed to replace a failed component with a part from a crate, a part from a different assembly, a different shift, a different fitter, you found the two were not quite the same. Not quite, and not quite. On a muddy road in Normandy at 2 in the morning is the beginning of a maintenance log that runs to 367 confirmed defects. British armor ran on fitted parts. American armor ran on interchangeable ones. That difference, multiplied across an army, a campaign, and half a dozen fronts, is what Exercise Dracula measured. The Cromwell was Britain's best attempt to build past that problem. It was a serious attempt. The design philosophy was speed, 32 miles per hour governed, over 40 ungoverned, faster than anything the British Army had fielded before, low-slung and lean, built by engineers who correctly reasoned that a tank which couldn't be acquired as a target was better than one that could absorb a hit. The Christie suspension beneath it was sophisticated. Long spring travel, high-speed handling. On good ground, the Cromwell was spectacular. The men who built it believed they had built something that worked. The engine they chose was the Rolls-Royce Meteor. On paper, it was the right answer. It came from the Merlin, the same V-12 that pushed Spitfires over the Channel and Lancasters over the Ruhr. One of the finest aircraft engines ever built. For the tank adaptation, the supercharger was removed, cutting output from 1,300 horsepower to approximately 600. Still 50% more than the Liberty engine inside the Centaur. Still the biggest leap forward British tank propulsion had seen in years. W.A. Robotham and Henry Spurrier, the engineers responsible, knew they were handling something important. They were also beginning to understand they had inherited problems the original Merlin had never been asked to solve. Adapting an aircraft engine for a tank puts two mechanical worlds in direct conflict. An aero engine knows one life. It accelerates, cruises, descends. It never stops suddenly. The Merlin was built for steady, predictable loads. The physics of flight. Most production Merlins also turned the wrong direction for a tank gearbox, which meant new camshaft lobes and a significant redesign on a timeline with no margin. These were not small fixes. They were problems built into the Meteor before a single Cromwell left the yard. And then, a 28-ton tank stands on the brakes. The loads a Cromwell driver generates, braking hard on a downslope, reversing over rubble, all pivoting on a tight corner, are forces an aero engine's internals were never designed for. Every hard stop stressed components built for a world where hard stops don't happen. Then came the heat. The Meteor was installed. The factory test was passed. The Cromwell was fast, genuinely fast, and the engineers signed off. The paperwork was filed. It was declared ready. Then they drove it in the field. Almost immediately, something started going wrong. A 27-liter V-12, derived from an engine designed to fly through open sky, was now sealed inside a low-profile hull with fixed ventilation and 5 crewmen generating heat beside it. The Cromwell ran hot, not occasionally, It was a characteristic of the engine in its new environment. It took 9 months to get it under control, partially. 9 months of field complaints, the redesigns, and 2 engineers who no longer believed the problem was solved. The Centaur, running its obsolete Liberty, had managed 8,000 miles before the trial loaded it onto transporters. The Meteor's predecessor, already past its useful life, couldn't finish the course. The Cromwell itself was overheating in the field. The Meteor engine would eventually find its place in history, but not yet, and not in this machine. Which left a question British industry was not quite ready to ask. If this was the answer, Rolls-Royce technology, the country's best engineers, its finest workshops, where else was the solution coming from? It would not come from Birmingham. It would come from a city that had never built a tank. A city that built cars. That city was Detroit. Oh, and what Detroit achieved between 1940 and 1945 was the most important industrial shift of the war. Not because Americans were better engineers, because they had been building toward this, without knowing it, for 30 years. The difference between Detroit and Birmingham wasn't talent. It wasn't patriotism, money, or worker dedication. It was process. Specifically, who had spent 30 years designing a system where the process mattered more than the craftsman. The story starts with a man who had never built a tank either. Albert Kahn was an architect. Born in Germany, trained in Detroit, he had spent his career designing the buildings that American industry worked inside. His first major commission was Highland Park, the Ford plant where Henry Ford introduced the moving assembly line in 1913. Kahn's buildings weren't incidental to what happened inside them. They were designed for production. Wide bays, column spacing calibrated to the rhythm of moving parts. Floor plans built around the sequence of components, arriving in order, and leaving as finished products. The building and the production system were the same thing, expressed in different materials. When the U.S. Army needed a facility to mass-produce tanks, they called Kahn. He designed the Detroit Arsenal at Warren, Michigan, in 11 months. One building, 5 city blocks long, built for one purpose, produce one vehicle, at scale, without stopping. It opened in 1941. By December 1942, it was turning out over 900 Shermans a month. One finished tank every 48 minutes, around the clock, 7 days a week. The paint on some hulls was still tacky when they went onto the rail cars. 900 a month, from one building. That exceeded the combined tank output of several European manufacturers during the same period. But the number alone doesn't explain the Sherman's reliability. What does is the philosophy the building was designed to house, and what that philosophy did to the concept of a spare part. In a Birmingham workshop, a craftsman made a component fit. He filed it, adjusted it, measured it by eye, worked it until it seated. The result could be excellent, and often was, but it belonged to that machine, fitted by those hands. In a Detroit facility, the question was different. How do you build a part that fits every time, everywhere, without anyone making it fit? The answer was the go-no-go gauge, a fixed tool. 1 second. The yes or no. Part passes, it goes in. Part fails, it goes back. No filing, no judgment at the assembly station. Parts built to that standard at the Chrysler plant in Detroit, at Fisher Body in Grand Rapids, at Pressed Steel Car Company in Chicago. All of them mated to any Sherman hull, from any factory, without modification. A turret from one state bolted to a hull from another, because both had been built from the same drawings, checked against the same gauges. The system took the craftsman's hand out of a chain that, in British armor, depended on it entirely. Chrysler, Ford, and General Motors didn't invent this for tanks. They had been refining it for automobiles since before the First World War. What they brought to the Sherman program was 30 years of practice at building identical things at volume, and the factories to do it at a scale British workshops had never needed to reach. The report produced decisions. British armored regiments would receive Shermans, not as backup, not as a reserve option, but as frontline vehicles alongside or replacing their existing tanks. The directive was worded carefully. The reception was not. Major Ronald was among those who took delivery of a Sherman and didn't hide how he felt about it. An experienced armor officer with no affection for American equipment, his first assessment was blunt, too tall, 9 feet from track to commander's hatch. The silhouette was wrong. It stood on open ground like something that hadn't tried to hide. A slab-sided box that announced its position from 3 fields away. Men trained on the Cromwell's lean profile found the Sherman ungainly. Ronald's phrase for it was direct and accurate by one measure: a high box on tracks. Most British armor officers who took delivery in 1943 and early 1944 agreed. The American tank was ugly, and everyone knew it. That assessment was reasonable. It was also incomplete, and Major Ronald, honest as he was skeptical, would revise it. But before his revision came a number, a single measurement that would become the most important specification in the Allied tank program. The Sherman's turret ring, the opening the turret seats on, measured 69 inches across. The Cromwell's measured 60. The 9 inches, buried in an engineering document among hundreds of other numbers. In 1943, nobody was writing memos specifically about those 9 inches. By 1944, those 9 inches determined which tank on the Western Front could kill a Tiger. The 17-pounder anti-tank gun, Britain's most effective weapon against late-war German armor, needed a turret ring wide enough to take its breach. 69 inches could take it. 60 inches could not without redesigning the hull from scratch, which the war had no time for. The result was the Sherman Firefly, an American hull, a British gun, the most dangerous Allied tank killer in Normandy. It wore American bones because American bones were the only ones wide enough. 9 inches, a footnote in 1943. The difference between killing a Tiger and not in 1944. The Detroit arsenal kept building, 900 a month. Every hull ready for any engine, every turret ready for any ring, every part built to a standard that didn't need a craftsman's hand to make it fit. And somewhere, in a sealed railway car heading east, 2 of those Shermans, rolling alongside a Cromwell, were on their way to Kubinka, outside Moscow, where men in Red Army uniforms were preparing to evaluate, all 3 with nothing invested in the answer. These men had no diplomatic obligation, no national pride at stake, no reason to soften anything. They would write down exactly what they saw. The Soviet test facility at Kubinka sat 40 miles west of Moscow, on a flat stretch of ground used for military evaluation since the 1930s. The engineers there had tested captured German armor, domestic prototypes, and now, in September 1944, 2 Shermans and a Cromwell. They drove them, measured them, recorded fuel consumption on asphalt, dirt road, and cross-country terrain, assessed armor, firepower, crew space, and mechanical behavior. Then they wrote their report the way Soviet technical assessment always wrote, plainly, without softening. The Cromwell 4, serial number T187888, consumed 225 liters per 100 kilometers on paved road, 353 on unpacked dirt, 370 cross-country through mud. The Sherman M4 A2, 180 liters on asphalt, 200 on dirt, 230 cross-country. For reference, did the Soviet T-34, the standard the Red Army measured everything against, consumed 170 liters on asphalt, 185 on dirt, 200 in mud. The Cromwell was thirstier than the Sherman by 45 liters per 100 kilometers on a good road. In mud, the gap opened to 140 liters, close to half an additional fuel tank, burned to cover the same distance. For an army built around deep strategic penetration, armored columns driving hundreds of kilometers into enemy rear areas before resupply could reach them, fuel consumption wasn't a preference. It was a problem that got worse the longer the campaign ran. The Soviet verdict on the Cromwell's construction was equally direct. The riveted hull was obsolete. The Red Army had abandoned riveted construction in the T-34 specifically because rivets, under ballistic impact, tear loose and become secondary projectiles inside the crew compartment. The evaluation report noted, in the dry language Soviet technical prose favored, that the Cromwell's designers appeared to have no knowledge of the T-34 and its sloped armor. Coming from men who had been fighting German armor since 1941 at the cost of their own people, this was not a professional courtesy. Tank T1 87888 was not returned to British service. It stayed at Kubinka. Nobody knows what became of it. It had served its purpose. The Sherman's assessment was different, not because the Soviets were generous, but because a man named Dmitry Loza had been filing field reports long before Kubinka that said the same thing from inside the vehicle. Loza was a Soviet colonel who commanded Lend-Lease Sherman units on the Eastern Front and later wrote a memoir, the most detailed first-person account of American armor recorded by a Soviet officer. He wasn't sentimental. He wrote about the Sherman the way a working mechanic describes a reliable truck, not with admiration for its looks, but with the specific appreciation of a man who has driven something that breaks and has now been handed something that doesn't. Two things stand out in his account. The first was the auxiliary power unit. The Sherman carried a small secondary engine that kept the electrics running without turning over the main power plant. At -32 degrees, on the Russian steppe in January, this was not a comfort feature. -32 outside the hull. The Sherman's APU ticked over. The electrics warmed. The engine caught. In a T-34, you might still be cranking. 45 minutes of cold weather struggle before the engine started in temperatures that turned lubricating oil to something closer to paste. The Sherman crew was already moving, while their counterparts were still at the crank. Loza's men knew the difference by the count of mornings they spent not cranking. The second was heat. The Sherman's crew compartment ran warmer than its Soviet equivalents. Not much, but enough. Men could freeze in a cold tank. Everyone knew it. A tank that kept its crew functional between engagements arrived at the fight with a functional crew. Loza's men gave their Shermans names. That's what soldiers do with equipment they trust. That trust traced back to something specific. The echelon repair system worked like this. Unit mechanics, second echelon, handled component replacement, failed bogie wheels, damaged track sections, radio failures, electrical faults. Mechanics trained on the same parts, using the same tools, following the same steps. The component came out, the replacement went in, and it fitted the way a key fits a lock that was cast for it, not cut for it. The replacement didn't need adjusting to match its host. It had been manufactured to the same specification as every other part of its type. Same tolerance, whether it left the factory in Detroit or Ohio, in March or August. Not similar, the same. If the damage ran deeper, engine failure, transmission hit, major hull damage. Third echelon took over. Maintenance battalions with heavier equipment and more expertise. But the logic held. The engine coming out and the engine going in were interchangeable by design. That was the point. A Sherman's engine weighed roughly the same as a Volkswagen Beetle. A trained crew with a gantry could have it out, swapped, and running again in approximately 4 hours. No craftsman required. No original assembler consulted. Any qualified crew, any crated engine from any depot. 4 hours, and the tank was back in the column. The same job on a British or German tank, engines hand-fitted to specific hosts, could take several days. Not because the mechanics lacked skill, because the parts weren't identical. They were close, similar, not the same. Not the same means you need someone to make them fit. That takes days, not hours. 4 hours against several days. In a campaign measured by how fast armor could exploit a breach before the enemy closed it, that difference showed up not in maintenance reports, but in how fast the column moved. Major Ronald had complained the Sherman was too tall. He was right about the height, a direct consequence of the radial engine at the Sherman's core, whose cylinder arrangement demanded vertical clearance that a diesel or multibank could avoid. The designers knew the cost and accepted it because the radial offered what the alternatives couldn't yet promise: proven durability, standard production, and the reliability baseline the program needed from day one, not 2 years in. But the height paid a dividend nobody had planned for. From 9 feet, a tank commander's eyes sat 3 to 4 feet higher than his counterpart in a low-profile vehicle. 3 to 4 feet across rolling terrain, translated into several hundred yards of visible ground. Several hundred yards to spot a contact, assess a threat, and decide before the enemy found him first. In the bocage, in the Pacific, on the approach roads of the European plain, that advantage arrived before every contact instead of after. You can't put it on a specification sheet. In a turret, it's decisive. The Sherman's adaptability showed itself most clearly not in what it was, but in what its crews made it. Sergeant Curtis Cullen was a mechanic with the 102nd Cavalry Reconnaissance Squadron. In the summer of 1944, he looked at the bocage, the ancient earthen hedgerows, the 3 to 5 feet of root-bound bank lining every field in Normandy, and solved a problem that had been stalling the Allied advance for weeks. When a Sherman tried to cross a hedgerow the standard way, its bow lifted, exposing the thinner belly armor to any gun across the field. Crews had been dying in that moment since the landings. Cullen's solution was 4 feet of angle iron, welded to the lower glacis, steel teeth that bit into the base of the bank, and drove the tank through at ground level, rather than over it. The material came from Rommel's own beach obstacles. Iron stakes planted at the waterline to wreck landing craft in June were cut down, hauled inland, and welded to the machines that needed to keep moving in July. 4 feet of repurposed steel, cut from the things meant to stop them at the waterline, now pushing them through Normandy's hedges. No factory kit, no directive from a depot. Unit mechanics with cutting torches and scrap German iron, working on a chassis standard, enough to accept the modification across the fleet. By the eve of Operation Cobra in late July, 60% of First Army's tanks had been fitted, 6 in 10, from enemy steel, without a single specialist part. A standardized, reliable machine is a platform. The men running it have energy left over for ingenuity, because they aren't exhausted keeping it alive. An unreliable machine consumes that energy, just staying operational. Nothing is left for anything else. Priestley's report documented exactly where that surplus went in a Cromwell unit. Captain Priestley compiled, with quiet administrative thoroughness, the specific human cost of keeping Cromwells running, brake adjustments that couldn't be safely done cold, procedures that required the housing to be hot, which meant fitters working on surfaces that burned whatever touched them, arms, hands, necks, the parts of a man that made contact with the housing when feel replaced instruments. He listed the delays. Objectives reached 4 hours late. Infantry that had moved without armored support because the Cromwells were still on the road, still behind, still being worked on, while a mechanic adjusted something in the dark that should not have needed adjusting. Captain Priestley named names. He documented precisely what it cost a Cromwell crew to do their job. But there is one entry in his report that has never been widely quoted. It describes a single moment, a single man, on a single night in September 1943. That entry comes later. Priestley's entry reads as follows. On the night of September 23, 1943, the morning after Exercise Dracula concluded, a Royal Armored Corps fitter was adjusting the brakes on a Cromwell that had not been allowed to cool. He had to touch the housing to do it. He worked by feel. The housing was still hot. He finished. He did not stop. The entry does not record his name. It records the burns on his hands, his arms, his neck. It does not record whether he said anything. The work was done, and the brakes needed adjusting before the metal was safe to touch, because the tank was needed and the column wouldn't wait for it to cool down. The entry is 14 lines long. The burns occupy 3 of them. That is what 0.07 maintenance hours per mile costs. Not a ratio on a page, but a man, kneeling on gravel in the dark, on the morning of a day that has not yet started, putting his hands on something he knows will burn him, because the machine requires it. And the alternative is a tank that isn't ready, and a unit that isn't whole. Major Ronald had driven both tanks. After enough time in each, revision wasn't diplomacy. It was arithmetic. He had called the Sherman a high box on tracks, and meant it. He revised that judgment, not because the box had gotten shorter, but because the box arrived. His conclusion, put in writing, was precise. A Sherman commander could rely on approximately 99% of his strength reaching an objective. A Cromwell commander, through no fault of his crews, through no failure of competence, through the mechanical character of the vehicle itself, operated in a continuous state of anxiety, 99% against continuous anxiety. That is not a preference. That is an operational assessment made by a man with nothing to gain from being generous to either tank. The summer of 1944 proved it. Operation Cobra launched in late July. Patton's Third Army activated on August 1st, and what followed was an armored advance that moved faster than the Germans could respond to. 800 miles in 3 weeks, through Brittany, east and south across France toward the German border. Tanks get knocked out. That's how it works. But the fleet held as a formation, because vehicles that broke down were repaired and returned, And the column was never stopped by its own maintenance for long. An army that moves at that pace needs machines that keep moving. The Sherman kept moving. That winter, the machines were asked for something other than speed. The Cobra King was an M4, A3E2, the jumbo variant, carrying additional armor plate thick enough that German gunners had taken note. It led the 4th Armored Division toward Bastogne on December 26, 1944, during the relief of the 101st Airborne, surrounded for 9 days. The Cobra King was knocked out on the approach. It was recovered. Mechanics went to work, parts replaced using the interchangeable system Detroit had built in from day one, and Cobra King returned to the column. It was present at the relief. One tank, out of the fight and back in it, but placed at the moment that mattered. This was not exceptional. It was how the system was supposed to work. Marine Corps assessments from Iwo Jima and Peleliu recorded an 80% recovery rate for knocked-out Shermans. Vehicles hit, immobilized, and returned to service across volcanic terrain, on supply chains as thin as any the war produced. 80% on black rock and ash, in a campaign that had not been kind to anything mechanical. The Sherman recovered from a Pacific battlefield is the number made real. A specific hull rebuilt, a specific crew back inside, a specific tank returned to the line. The Meteor engine found its correct home in the end. Robotham and Spurrier had been right about the engine's potential, wrong about the timeline and the vehicle it needed. The Centurion entered service in 1945 with the thermal problems resolved, the torque issues corrected, and 9 months of hard experience built into a chassis designed from the beginning to hold a 27-liter V12 rather than bent to accommodate one. The Centurion served in a dozen armies across 4 decades and became one of the most capable tanks ever produced. Britain had learned. The cost of that learning, in broken vehicles, in reports that went unheeded for 2 years, in the exercises and letters from Washington and trials called Dracula, was high, but the learning was real. For this war, it came too late. For the next generation of soldiers, it was ready. The Sherman was not the finest tank of the Second World War by any technical measure. Its gun was adequate. Its profile was a liability in the open. Its vulnerability to the best German weapons was real, and the men inside knew it not from reports, but from the moment the calculation went wrong. None of that is in dispute, but it was there. That is the one thing it was. There when Patton needed the column to keep moving. There when the 4th Armored needed a tank back on the Bastogne road. There when Loza's men needed an engine to start at 32 below. There when a hull had been knocked out on volcanic rock and a crew needed something to climb back into. It made the promise. At the drawing board, in the go, no-go gauge, in Kahn's 48-minute production cycle, and it kept it. In total war, that promise is worth more than any specification ever written. The unnamed fitter in Priestley's report never read the 0.03 against the 0.07. He never read Richardson's letter or Loza's memoir or the Soviet assessment of serial number T-187888. He wasn't in the meetings where Major Ronald revised his conclusions. He wasn't in the offices where the Detroit Arsenal's numbers landed and men understood what 900 a month actually meant. He was in a field in Bovington on a September morning before the sun was up, with his hands on a brake housing that had no business being touched yet. He did it anyway. The burns healed. The tank was ready by morning. His name is not in the record. His hands are.